Okay, well, thank you. It's my pleasure to introduce Varundev Suresh Babu from University of Virginia, who's going to tell us about the ROS F1 10th Scale Autonomous Racing Simulator.
Hello, everyone. I'm here to talk about the ROS F1 10th Autonomous Race Car Simulator and how you can get started with this lightweight yet robust autonomous racing simulator. I would like to start by thanking the ROSCon organizers for this opportunity to share my work with you. My name is Varundev, and I'm a PhD candidate in computer engineering at the University of Virginia. I'm also one of the principal authors of this autonomous racing simulator. Before I tell you about the F1 10 simulator, I would like to know how many of you in the audience have heard of the F1 10 platform. Okay, some. So what is this F1 10th I keep referring to? The F1 10th, or F1 by 10, is a fully autonomous Ackerman steering race robot inspired by the Formula One race car. It is literally 1/10 the scale of an actual race car, although it is 1/10 the scale of the original race car, based on my own personal experience and that from the community. I can say that it's 10 times the fun. So the F1 10 platform is designed to make vehicular autonomy easily accessible, and it's fully capable of implementing the perception, planning, and control pipeline online and in real time. It is the quickest way to get started with autonomous racing. I and the other maintainers of the F1 10th project have been working on the platform for over 5 years now, and we have created a repository of information on how to build, code, and race the F1 10 autonomous race car. We have made the project open source and freely available on our website, f110.org. I encourage you to visit the website to learn more about the project and get started with your own F1 10 build. A few notes about the F1 10 hardware. When choosing the race car chassis, we emphasize the need for a drivetrain capable of rapid acceleration and fast cornering. The best fit for the project was the RC race car manufacturer chassis. The left half of the slide here shows the chassis similar to the one which we use for the F1 10th, and the right half shows you the chassis used by Tesla for its Model S. The key message here is that these platforms have similar dynamics, just different parameters. Along the same line, the sensors we use for autonomous navigation are not dissimilar to the sensors being used in full-scale self-driving cars. In this picture, this is the F1 10th, along with its cousin, the NVIDIA full-scale self-driving car. The F1 10 platform supports a variety of navigation sensors, including scanning LiDAR, depth camera, stereo cameras, and inertial sensors. If a sensor is provided with a ROS driver, we test it right away for its fit in autonomous racing. Other critical elements of the F1 10 platform include a central Linux computer, a radio telemetry station, and a chassis controller. The current version of the F1 10 race car is powered using an NVIDIA Jetson TX2 embedded computer, which has proven itself to reliably deploy complex navigation algorithms. For the chassis controller, we use the VESC skateboard controller, which is in the lower right of the screen, right here. This controller is capable of running both the traction motor and the steering servo. The ROS package accompanying the skateboard controller also provides critical odometry information that is necessary for high-level path planning. This slide is a little busy, and I'm happy to go over it at the end if anyone's interested. But what I want to emphasize over here is the F1 10 platform is an ecosystem consisting of a variety of disciplines. It forces you to think about the multiple aspects involved in designing a system. This can be easily seen where the F1 10 platform is used for a variety of ROS-based autonomous navigation research. A few examples of the kind of research enabled by the F110 include the traditional open loop navigation like follow the gap method, implementing a model predictive controller, using the F110 as a means to collect training data for training a DNN network and then later verifying the performance of the resulting model, and also some vehicle-to-vehicle communications as well. A few more examples of fully closed-loop autonomous navigation include the implementation of lane keep assist, and also the traditional ROS SLAM packages and ROS navigation packages. But what is the use of an autonomous race car without an autonomous racing competition? Today, I am proud to say that the F110 community has a rich legacy of organizing autonomous racing competitions at least twice a year alongside major academic conferences. Teams from around the world compete in what is essentially a battle of algorithms amongst vehicles that have a similar hardware. Now, a quick video. So I was hoping there was sound, but unfortunately no. So as a race car completes this loop, you will notice that it's going at such high speeds that when it turns, so what I wanted to show from this footage, from this onboard footage, is that the vehicle navigates around the racetrack very fast. So mechanical design always took second priority when we were building the F110 race car. But now that we are at a stage where the cars travel autonomously at such high velocities, we have to work on aerodynamics and issues like downforce. Some of the design elements that we could comfortably ignore until now. Here is another video of two autonomous race cars, and the camera car is trying to overtake the car in front of her. Now both of these cars are fully autonomous. They're running very different controllers. So, they also have active collision avoidance. You'll see the car trying to overtake the other car from the inside, just like a human-controlled race car. The autonomous overtake here happens much closer to the apex of the racetrack. So from being used as at a handful of universities, the F110 is now used at over 24 universities in North America. Most major research universities use the F110 platform, both as a teaching tool and for research. Our community partners are also present in Europe and Asia, and new members are being continuously added. Even our internal development issues are shared with the community, and their active feedback helps the platform evolve every year. Unfortunately, the F110 platform has some drawbacks. Although we have tried our best to design the F110 car using affordable sensors and computers, the bill of materials needed to build the race car currently stands at around $3,000. This price increases significantly based on the final design considerations. The price point of $3,000 makes this race car unaffordable for the majority of research groups around the world. Even if they can afford it, there is a significant time difference between building the hardware platform and implementing the algorithms that make it a true autonomous race car. To help the teams which are facing either of these issues, we have introduced the ROS F110 Autonomous Race Car Simulator. This simulator is entirely open source and made available to all those who are interested in autonomous racing. So please visit our website, f110.dev, to learn more about the simulator. So the F110 simulator is based around ROS Melodic at its core, and it requires Ubuntu 18 and Gazebo 9 to work on your local machine. Instructions on how to install the simulator and tutorials to help you get started with the F110 racing are made available on f110.dev. In this video, I am running a keyboard teleop session. If you like the videos you see on the screen, and if you're interested to run it on your local machine, use the command at the bottom right here to run the demo locally. For all videos henceforth, the commands will be displayed at the bottom of the slide if you want to run them locally. The simulator itself consists of 3 critical elements required for autonomous racing. I will provide a brief overview of these elements as we go forward. The first element is the virtual race car, followed by the virtual racetrack, and finally, the algorithms needed to drive the car around the racetrack autonomously. Here's a brief overview of the working elements of the ROS F1 10 autonomous race car simulator. These elements can be broadly divided into 3 blocks. The first block represents the simulator's front end, consisting of Python scripts and APIs that control the simulator's parameters. Also at the front end is an XML file describing the virtual race car and its properties. More of this in a bit. The second block is the core, consisting entirely of ROS and ROS-based packages, including SLAM and navigation. The control package of the real F110 race car is also embedded in this block to make integration easy and the code portable directly to the actual F110 race car. The actual simulation happens in the third block within Gazebo. RViz configuration files for most traditional ROS packages used in autonomous racing are also provided to help visualize data in real time. The virtual race car is a model created by observing the performance of the real F110 race car. We take the ranges of speed, cornering, acceleration, and braking as observed from the real hardware and encode it as a macro file along with a 3D mesh that visually represents the virtual race car and how it looks in Gazebo. To remain true to our principles while designing the F110 race car, we have modularized the construction of the virtual race car as well. Finally, certain geometrical and mechanically equivalent constraints had to be applied to the virtual race car, including the implementation of Ackermann steering geometry and hard differential speed constraints on both wheels and on both axles. We emphasize the modularity in our designs, but we also understand that certain critical elements must always remain in place. One such element in our simulator is the 2D scanning Hokuyu type LiDAR at the roof of the race car. This is the primary navigation sensor, and the race car nodes will not allow the car to move in the simulator if the scan topic is not available. On the hood of the virtual race car, there is a unified sensor block consisting of cameras, radars, and inertial sensors. All our individual sensors can be enabled or disabled by setting the appropriate flag during runtime. Finally, the virtual chassis consists of visual and functional objects and frame links necessary for autonomous robot. Features of the chassis include the presence of an all-body contact sensor and powertrain management tools. To get the virtual F110 race car moving, we have created a control plugin node. This node is responsible for the static TF links between the car and its sensors. The example being the base laser link and a dynamic TF like the base odom link necessary to keep track of the race car and make autonomous navigation possible. The control plugin also translates various navigation stack output to a format understandable by the race car. Here is the node graph showing a teleoperation of a single race car. The control plugin is at the center of nodes between the control and the simulation in Gazebo. Some more information about the command part of the control plugin. The controller accepts command in the message type called Ackermann drive. If your navigation stack outputs a traditional command velocity twist type message, the F110 simulator contains a node to translate that to Ackermann drive. The first type of control is implemented on the front axle to adjust the displacement of the steering column so that the vehicle can turn according to the underlying Ackermann steering geometry while in motion. The second type of control is to set the RPM of the wheels using a PID type controller. Depending on configuration, the wheel RPM control is implemented on the front axle, the rear axle, or both by default. The TF tree looks like that of a generic ROS mobile robot base. The right half of the slide shows an annotated image of the various frames involved and their respective locations. In keeping with conventions, the base link of the virtual race car is at the center of the rear axle. The position of the map frame and the initial pose are set manually for each new environment. To create a race car in an active gazebo session, or to launch a race car at the start of the simulation, the following template is used. At first look, it looks no different than those used for a generic mobile robot. Some new parameters have been introduced, but the following properties have to be set. The car name parameter is a ROS-compatible alphanumeric string that is both used to identify the race car and to resolve namespaces in case multiple robots are being used. This name is unique to an active race car. The car paint parameter sets the color of the visual 3D mesh that appears as the body of the virtual race car. This is purely visual as of the current simulation release, and it can be used for object recognition nodes in the future releases. The run gazebo parameter is very important because it launches the gazebo simulator only once at the beginning, and any subsequent spawns of the race car do not destroy the current gazebo session. So it is, in essence, a circuit breaker. The position arguments control where the race car is spawned relative to the origin of the odometry frame and provides a planar constant offset to help aid the race car trackers. A novel feature of the F110 simulator is its ability to spawn multiple race cars. Each race car has its own namespace for parameters and ROS nodes, and the resolution of this namespace is handled internally by the simulator. You would just need to provide a unique name for each car, and it will become its own namespace. The node graph on the right shows the control nodes of 3 different race cars neatly resolved by the simulator. The TF tree of multiple race cars have 2 common elements, the map frame and the odom frame. The relationship between these frames is static for our simulation. The frames exist only to satisfy the requirements for traditional ROS navigation packages. I will talk more about why why the relationship between these frames are static in the upcoming slide. Here is a gazebo view of the racetrack that is included by default with the simulator. The racetrack was designed in-house and contains a healthy mix of straight stretches, turns, and short corners. You can use your own racetrack in the simulator. All you would need to do is draw a racetrack in 2D, use a CAD software to convert it to 3D, and export an STL mesh. The website contains information on how to include a custom racetrack in the F110 simulator. Within the racetrack, the drivable area is an asphalt plane with the boundaries demarcated using the STL file. The yellow race car shown right here is for scale. The accompanying RViz configuration files provide the visualization parameters necessary to verify the performance of your algorithms. The first-person view of the race car, shown in the lower left, was used to collect data for training a machine learning model. The F110 simulator has been fully integrated to work with major ROS SLAM packages. The video on the screen shows Hector mapping in progress while the race car is being teleoperated. The commands at the bottom are all it takes to get this demo working on your local machine. High-speed racing requires high-speed localization. This is one of the reasons we could not use AMCL and why the map and the odom link are static. What we use instead is a GPU-powered particle filter. The commands at the bottom are what it takes to get this demo working on your machine. The TF tree showing the static link between the map and the odom frame because the particle filter directly publishes map to base link. Here is a video showing ROS navigation implemented with the help of a TEB local planner. Even after properly tuning the navigation stack, the higher speed of the race car and its dynamics, the traditional path planning algorithms generally fail. If you notice a race car at turns, it overshoots the planned path and almost collides with the track boundaries. Here is the TEB navigation implemented on multiple race cars. While the race cars are trying to actively avoid each other and continuously replan trajectories, you'll notice a collision right here. We try very hard to not make them collide, but because of the sheer speed of the race car, they're not able to maneuver fast enough to let that happen. To overcome the limitations of traditional path planning algorithms, especially when it comes to high-speed autonomous racing, we were forced to revisit the basics of physics, control systems, and design of algorithms. This video demonstrates one such result, where we used pure pursuit control with adaptive look-ahead distance and a global race line. The lowest speed in this video was over 2 times the average speed observed using traditional navigation packages. Here is another video showing the same race controller implemented on multiple race cars. The cars were spawned at fixed distances away from each other. They appear to be as a convoy with vehicle-to-vehicle synchronization, but they're not. They are independent and completely decoupled. So, in conclusion, we have created an autonomous racing simulator based around the F1 10th platform, which uses ROS and Gazebo as its core elements. We have tested our algorithms on this simulator, and it has given us a good benchmark for verifying the performance of a racing controller. We wish to share this simulator with the rest of the robotics community, so we have open sourced it completely. Our source is freely available on GitHub, and we are working with AWS on deploying it with the RoboMaker. That's it from me today. Visit the f110.dev to get started with the simulator today, and I'm happy to answer any of your questions.
We have time for a couple of questions. There's a floor mic in the middle of the room back there, or if you're close to me, I can hand you this one. Okay, we'll go to Cam.
So if you could add a little bit more on the GPU particle filter acceleration, is that natively in the master packages, or you guys added that?
Can you repeat that, please?
The GPU acceleration for the particle filter.
Yes.
Is that natively on the main packages, or you guys contributed that?
So the GPU particle filter was developed originally by the MIT race car team, especially to work with the F1 10th platform. It is not a standard ROS package, but it is available freely to download, and it comes as a core package when you download the F1 10 simulator.
Other questions? Yep.
Just now, we have some explanation about fleet management. How will you comment if I want to use this racing car system in an AGV system in a factory? Will it be much faster?
So it's not a very, there's no easy answer to that. I do want to say the reason why we work in autonomous racing is to ensure agility in autonomous systems. So high-speed racing makes the vehicle experience the edge cases which you would not usually get even if you drive 1,000 miles. So through autonomous racing, your system, training your system through autonomous racing can provide a higher level of safety. So I would, to your question, the answer is generally yes, but I don't know what else to say. Sorry.
All right. Okay, last question. I think you can just come up to the floor mic in front of you.
So does the software drive faster than humans or slower than humans?
Generally faster than humans. Yes.
All right, well, thanks again.